Erin's going to continue on the talk about CMIC's processing portfolio, a really interesting project related to microwaves that happened through a project development workshop that CMIC led a year and a half ago. The question, and it's really interesting, the question was raised that why are we bothering with microwaves? We've been trying for 30 years, it's not going to work, we should stop now. When a group of people at that workshop that had never worked together before said, well, why not? And Erin's going to be talking to you a little bit about how we believe this project is going to solve the issue of how we can use microwaves in more ways than one. Little quick bio for Erin. She's a professor in materials science and engineering at U of T. Her research spans mineral processing from comminution to tailings. And aside from her academic pursuit, she spent 2 years at Intel and over 3 years at Valley. So Erin, the floor is yours.
Great, thanks so much, Carl. So as stated, I'm just going to provide an update on the CanMicro project, which, like the CAM, is also a finalist in the Crush It Challenge. So CanMicro is about moving beyond historically used comminution strategies to apply energy to ores in an alternate and efficient way. We've combined existing microwave and sorting technologies to break particles where desired and to sort valuable particles from waste for maximum comminution energy savings. The heart of the project is scalable multi-mode microwave technology that can be seamlessly integrated into existing mining operations to achieve energy reductions of up to 70%. The overall objective is to commercialize microwave technology for the mining industry. Here's an overview of the CanMicro process. After primary crushing, ore particles up to 150 millimeters are exposed to high-power microwaves in a belt-fed multi-mode system for a short time. Microwave exposure results in differential heating of grains within the ore, which generates thermal stress and cracking along grain boundaries. Typically, value minerals heat in response to microwaves, and the CanMicro process uses the thermal signature to sort value minerals from waste rock. Ultimately, the CanMicro process results in weakened ore particles, rejection of waste through sorting, a better liberated and higher grade feed for downstream processing, and a coarser final grind size, all resulting in significantly reduced grinding energy. In addition, there are substantial benefits for downstream processing, such as improved flotation, leaching, and gravity separation performance, as well as reduced tailings production. Together, all these benefits add up to significant energy savings. So a huge strength of our project is our multidisciplinary CanMicro team. The project is guided by the steering committee, consisting of myself as the technical lead, Jillian Holcroft of CMIC, who is the administrative lead, and who has played a really big role in supporting the project and finding new partners. Andrew Gillis of Sepro Mineral Systems, where the CanMicro pilot plant is located, and Dominic Fragamini of Glencore, who are providing technical and analytical support through XPS. Other consortium members include XPS, Azenco, Queen's University, Kingston Process Metallurgy, Corem, and the Saskatchewan Research Council. Together, this team has the skills required to take this technology from the bench scale through to commercialization. The timeline to achieve pilot demonstration of the CanMicro technology is 18 months, as dictated by the Crush It Challenge. Shown here is the original schedule. The project consists of 4 phases. Phase 1 is the bench scale assessment of ores to select samples for pilot plant testing. Phase 2 involves testing of the high-powered microwave system to establish optimal conditions for treatment. Phase 3 is the integration of microwave treatment with an industrial sorter for continuous automated sorting with multiple sensors. Phase 4, downstream testing, includes establishing the effect of CanMicro on downstream processes to capture the true energy savings. At this time, we are behind schedule. Originally, this was due to a delay in receiving funding, and now, of course, we are in the midst of pandemic. Currently, we're in phase 2, but although the pace has slowed, we are still progressing. So as stated, the first phase of the project has focused on the bench scale assessment of ores to determine which should be tested in the pilot plant. The bench scale testing, which requires a sample size of only 50 kilograms, consists of 4 components. The first is fundamental characterization, which includes ICP and XRD analysis to identify the elemental and mineral composition, and QuemScan analysis to assess ore texture. It also includes permittivity measurements to determine the dielectric properties of ores, which largely govern their microwave response. The second is microwave heating tests, which are conducted using a 3 kilowatt to 450 megahertz benchtop laboratory microwave system. Shown here is a test where we're seeing some arcing. So it's a little excitement in the lab. The third is combination testing. At the bench scale, this involves grindability tests to determine the work index of ores before and after microwave treatment. We also do QEM scan on the products to determine the effect of mineral liberation. Last is the evaluation of ore sortability. This includes exposing rocks to microwave for a specified length of time and imaging each rock after microwave treatment with a thermal camera. The elemental content of the treated rocks is then determined by ICP. So now I'm going to show some results from phase 1. So far, over 30 ores have been tested at the bench scale, and in fact, I think the last number I saw was 35 or 36, resulting in the creation of a large database of ore microwave response. And to our knowledge, this is quite possibly the largest database of its type. Shown here are some example permittivity and heating curves. The real permittivity, shown on the left, is the measure of how well the microwave field can set up in a sample, and the imaginary permittivity center really is a measure of how well a sample can turn that energy into heat. You can see there's a wide range of response. We have heating curves on the far right. We have some very good heaters with some steep curves and some that are less responsive. And this information gives us clues as to which ores are good candidates for CanMicro, and also provides crucial information on how quickly an ore will heat. And that information is really necessary for good control of the process. Next, we have some results from the grindability tests. Shown on the left is a plot of the work index of ores after microwave treatment versus the untreated work index. Data points that fall below the dashed line in the green represent a positive result. You can see that a reduction in work index after microwave treatment was observed for quite a few ores. In the middle, we have the increase in massive fines produced in a fixed time grinding test versus the work index. If the quantity of fines produced in a given grind time is increased by microwave treatment, the grindability is improved. Again, improvement was shown for a number of ores across a wide range of ore hardness, which to me is really exciting. And lastly, on the right, we have the massive fines produced in the fixed time grinding test versus the work index reduction. So positive results in both these types of comminution tests suggest the ore is a strong candidate for pilot plant testing from the comminution or the grinding perspective. Shown here are thermal images acquired from a mid-IR thermal camera. Note that different heating patterns are observed for different rocks, and these heating patterns can be correlated with the mineral composition. It is important to note we are not just looking at the temperature achieved, but rather at the heating patterns. And on the basis of these patterns, we develop sorting algorithms for each ore, which are then used for a hypothetical sort. In the middle plot, we have an example curve showing sensor response versus valuable content. We've had very positive thermal sorting results to date. They have exceeded my expectations with significant mass reduction while maintaining high valuable recovery. So on the right, we have sorting mass reduction versus work index reduction. And this is really how we chose the ores for the pilot plant. So ores that respond positively, both in terms of grindability and sorting. We requested the large 5-ton samples for the pilot plant. And now Andrew is going to give us an update on the exciting part of the project, which is what's going on at the pilot plant.
Hi, I'm Andrew Gillis with Sepro Mineral Systems. I'm here at Sepro's research facility in Langley, Canada, where we have a CanMicro high-powered microwave pilot plant installed. Let's go on into it. The microwave system consists of two 75 kilowatt generators that are run in parallel to supply 150 kilowatts of microwave power at 950 megahertz. Microwaves are transported via wave guide the microwave cavity, where the ore is introduced to the cavity by a microwave transparent conveyor belt. Several 5-ton samples of minus 150 millimeter material, arriving in buckets, bins, and barrels, have been supplied by mining companies for pilot plant testing. Samples are first crushed to a uniform size. Samples are then screened to determine the particle size distribution, homogenized, split into representative samples for pilot plant runs. We're currently treating material up to 75 millimeter. The design is scalable to rocks larger than 150 millimeter. At present, Microwave transparent polypropylene trays are used to introduce samples into the microwave cavity. The conveyor belt is outfitted with a VFD that can be run at speeds up to 5 meters per second, to ensure precise control of the sample load and to accurately determine the power input in kilowatt hours per ton. Industrial systems will be directly loaded. After microwave exposure, the rocks pass under an infrared camera to observe heating patterns. The samples then undergo testing to determine the impact of microwave treatment on the energy required for comminution. Different tests are used to cover the full range of particle sizes and breakage types found in crushing and milling circuits. The bond impact crushing test is used for particles greater than 25 millimeters. These tests are conducted at ALS Metallurgy in Kamloops, BC. The SAG design test developed by John Starkey is used for rocks 1.7 to 25 millimeters in size. Bond work index tests are conducted on the product of the SAG design test, which is minus 1.7 millimeters. The results of the comminution tests are used to model the energy use in crushing and grinding circuits with and without microwave treatment. For thermal sorting, rocks must be dispersed in a monolayer as they pass under the mid-IR camera. At present, hand sorting is being conducted to build the sorting algorithms. In the future, the pilot microwave system will be integrated with an industrial sorter equipped with a thermal camera, as well as other sensors, such as XRT and conductivity, to maximize sorting efficiency. With the high-power, multi-mode continuous microwave setup and characterization test suite of equipment all ready to go, we're now testing large ore samples and anticipate having pilot plant results later in the summer of 2020. Once we've optimized the microwave treatment to maximize energy savings, we'll move on to the next phase of the project, which is the integration of multi-sensor ore sorting with the microwave system.
All right, so as Andrew mentioned, the next phase of the project involves integration of the 150 kilowatt microwave system with an industrial ore sorter. And once installed, we'll shift from hand sorting to automated sorting with multiple sensors. Phase 4, downstream testing, including flotation, leaching, and gravity tests, as well as investigations into the impact of CanMicro on tailings, including the amount and quality produced, will begin this summer in parallel with Phase 2 and Phase 3. So in conclusion, CanMicro is the only technology to combine microwave-assisted comminution and sorting with energy savings of up to 70%. Phase 1, ore screening is complete, although we continue to test ores when there is interest. Phase 2, testing of the 150 kilowatt microwave, is currently underway at the pilot plant. Thus far, we have observed very promising results in grindability and sortability, and we're well positioned heading into the last 6 months of the Crush It Challenge. So I'd just like to thank the partners on the CanMicro team, as well as the mining companies that have supported us and supplied ores, as well as NSERC and Natural Resources Canada for funding through the Crush It Challenge. And I'm prepared to take any questions that you may have.
Awesome, thank you very much, Erin. Great presentation as always.